entire subject of motion under gravity. In fact, starting from acceleration and all the way we are going to study now projectile motion, all of these topics. Do you know who was the person who actually spent most of the time figuring this out? Galileo. Okay, Galileo did lots and lots of experiments. He lived for quite a long time. I think he lived up to 85 or 86 or 89 or something. And most of his living years, he did experiments in motion. Before Galileo, people had lots of misconceptions about how things move. For example, the idea was if I throw this ball, the ball moves because I am pushing. And as long as I am pushing, I am exerting a force. When I leave it, they assumed that whatever I was doing was going to continue. It was impressed on it. But over a period of time, this force will stop. And then it will fall down. So the assumption was projectile motion goes like this. Actually, it was more like it goes like this. And then there is some intermediate thing, then it does this. By the way, it looks like that. See, if I throw this ball, it looks like it was almost going straight, and then something happened in the intermediate phase, and then it was going down vertically. But actually it doesn't go vertically at all. If you plot it very carefully, it was never going horizontally, it wasn't doing this. This is not how it does. Actually what is happening is this is how it's moving. Except that the fall gets sharper and sharper, so to our eyes it looks like it is almost vertical. In the beginning it looks like it is almost horizontal. But Galileo spent a lot of time trying to understand and analyze questions like this by throwing many different objects from various heights. Okay, and the fact that he was able to then explain motion very, very carefully meant he could predict what is going to happen, and this became the starting point of modern science, all of modern science. So when you are learning projectile motion, remember you are not just learning projectile motion, you are also learning the basis of modern science, because modern science started with the first experiments on projectile motion. Till that point, the assumption was people will explain. They had some observation, they would explain some theory. They already had a theory before they had an observation. What Galileo did was to observe carefully and say, no, it never goes like that, it goes like this, and that theory doesn't explain it. So he reworked many ideas. For example, this assumption was that it will become faster and faster as it gets closer and closer to the earth. That means it was very slow there and it becomes faster there. Actually no, it has the same increase whether you are going from here to there or whether you are going from here to there. The speed is larger, but the rate of increase of the speed is the same. Galileo coined the word acceleration. Acceleration means it is the to add to velocity. You add velocity. You take a velocity and you increase it. Okay, which exactly what acceleration does. He also discovered that if I drop two objects, they take the same time to hit the ground. If I drop them like this, you can hear two different sounds. If I drop them like this, you hear one sound. Okay, but it's not surprising because both of these are tennis balls. So then he said, okay, let me drop this and this. But this fellow bounces off quickly, so just hear the first sound, because the bounce is not going to be equal. The first sound is what is going to be equal. Listen carefully. It happens at the same time. Okay? If I take this fellow and I take that fellow, they are both going to take the same time to hit the ground, wherever the ground is. It doesn't matter the ground is here. What if the ground was there? They will still take the same time. What if the ground was here? Still take the same time. How do you know? By dropping it from different heights, he was able to check this out. That means, do these fellows know, is it possible, for example, that this fellow was here and this ball was there? Then as it came closer to the ground, this fellow started speeding up and they came and hit the ground. Is that what is happening? So his argument was, this fellow does not know where the ground is. I can put wherever the ground is, right? I can decide to put the ground here or there or wherever I want to. Now, then that means that when this ball reaches this point, At that time, this fellow must also be here. Not just that it takes the same time to hit the ground, at every instant they must be moving by the same amount, and therefore they must be having the same velocity. The velocities are increasing, but the increase in velocity must be the same. They must have the same acceleration. Big object or small object, every object has the same acceleration. So you should make sure that the base is the same. So if I keep the base same and I drop it, can you hear that? It's just a single sound. So now let us start first with one simple case of uniform accelerated motion, and that is this ball being dropped. So if I drop this ball, is it moving with uniform velocity? No. What is the velocity at that point? 0. Okay, drop will generally mean 0. We will learn that it won't always mean 0. For most questions, we'll worry about it. Not when we get there, we'll think about it. At this point, drop means 0. But if it was 0 and it remains 0, where will it remain? There. So obviously, its velocity is changing. And you know that Galileo did a lot of experiments to show that it comes down with a constant acceleration of how much? 9.8 meters per second square. For most calculations, we'll assume that it's going to be 10 meters per second square. So we call it G, and we say G is 9.8 meters per second square, approximately 10 meters per second square. For all our purposes, we will just use 10. Now in the beginning, when I drop it, what is its velocity? 0 meters per second. It keeps coming down. So by the time, let's say, it reaches this point, it has a velocity. Let us say that this takes t seconds. What will be its velocity? 10t. Okay. Suppose I say that this was 4 seconds. How much is its velocity? 40. Suppose I tell you it's 3 seconds, 30. Every second it's increasing by 10. So in 3 seconds it will become 10 plus 10 plus 10, 30. Why? Because the beginning the velocity is 0. Okay. Now this is my final velocity. That is my initial velocity. What is my average velocity? 20. I don't need to calculate. It's simple, right? 40 plus 0 by 2. 20 meters per second for 4 seconds. But this is the average velocity. You know that average velocity into time must give me displacement. So what's the displacement? 80 meters. You can also write S is equal to ut plus half at square, but it's equally easy to say in 4 seconds it's become 40. 0 plus 40 by 2, 20. 20 into 4, 80. Just do a couple of things like this and then we are good to go. Okay, here I am going to drop this ball. Okay, I drop this ball. What is the velocity? 0. 3 seconds it takes to fall. Suppose 3 seconds later it hits the ground. What is the velocity here? 30. What is the average velocity? 15. How much time did it take? 3 seconds. So what is the displacement? 45. Okay? Okay. Now I drop this ball and it hits the ground with a velocity of 20 meters per second. I drop this ball, it hits the ground with a velocity of 20 meters per second. How long was it traveling? 2 seconds. Because this is 20, it must have been traveling for 2 seconds. Okay. Now it's taking 2 seconds. What is the average velocity? 10 meters per second. Why? Because the end velocity is 20 and that velocity is 0. So it is 10. 10 plus 0 plus 20 by 2. So 10 meters per second into 2 seconds. So what is this displacement? 20. Okay. I drop this ball, it hits the ground with 50 meters per second. 50. I drop the ball. I don't want you to use any formula right now, just quickly calculate. It hits with 50 meters per second. I want you to tell me the displacement. 125. How do you know? What is the average velocity? 25. How much time? How do you know 5 seconds? Because this is 50, that is 0. So that means it must have changed by 10, 10, 10, 10. So therefore 5 seconds, and therefore 125 meters. Now let us make this a little bit more messy. Okay, instead of dropping the ball, I now throw the ball. Now I throw the ball with 10 meters per second and it is traveling for 3 seconds. What do you think will be this? 40. What do you think will be that? 25 meters per second, because average velocity will be 40 plus 10 by, how do you get 40 meters per second? Because it increased by 30. What increased by 30? 10. 10 plus 30, 40. 40 plus 10, 50 by 2 will be average velocity. 25 into 3, 75. This is 75 meters. Clear? Simple enough to do this calculation. Okay. Idea is to never try and use a formula until you have put enough numbers. I know that there is generally a habit in physicists, mathematicians, teachers, textbook writers, everybody, to first tell you a formula, derive everything with letters, because you already know algebra well. And so once they put enough letters, then after that you start to substitute in the formula. What happens is, ultimately a formula is just a tool. If you know what you are doing, you can put T and A and whatever you want and calculate and find the formula. But if you start off not by doing this, but actually starting with the formula, what ends up happening is you have become dependent on the formula. You forgot the formula, you don't know what to do. Now there is no formula, you can't forget. What are you going to forget? There is nothing for you to forget. So if there is something for you to forget, then there is something you can forget. Okay, so you can't forget anything now. Anyway, let us put some formula like things now. It starts with 0. Let us say it travels for t seconds. What is its velocity? 10t. What is its average velocity? 5t. What will be the displacement? Now let us use the formula and show this. S is equal to ut plus half at square. U is 0. A is 10. So it is 5t square. Same thing. I am just saying that you already know, because that is 0, this is 10t, this must be 5t, 5t into t must be this. So why half at square? Oh, because you start with 0, you must have at as your final velocity. So half at is the average velocity, but you are traveling for t seconds. So half at square. Then why ut plus half at square? Because probably you are not starting with 0, you start with u, then you had not at but at plus u, and so average will be at plus nothing by 2 and u plus u by 2. What is u plus u by 2? U. So average velocity is u plus half at into t, ut plus half at square. Okay? Now you are going to use this many times. It's worth keeping in your head how it comes up in many different ways and where it's connected. So I hope everybody is clear about this now. Yes? Okay. Now you know that it travels 5t square in t seconds. Suppose a question says g was 9.8 and not 10. What will you do? It will be 4.9 t square. Why? 0, 9.8 t, average 4.9 t, t seconds, so 4.9 t into t, 4.9 t square, or half a t square, half 9.8 t square. Okay. Now that we know this, if I tell you I drop a ball and from a building of height 45 meters, okay, how long will it take to hit the ground? Three seconds. Why 3 seconds? Because this has to be 5t square. Why? Because this starts with 0. So you know that it's going to travel 5t square. So this must be 5t square. So t square must be 9, t must be equal to 3. So it's traveling for 3 seconds. What speed does it hit the ground with? 30 meters per second. Why? Because it's traveling for 3 seconds. Every second you are increasing by 10, 10, 10, 10, 30. because you started with 0. Everybody is following this? Okay. So the idea was he would take two objects, let us say one small object and one large object, and the large and small doesn't really matter. Okay. He threw these two objects, not dropping them like this, but he threw them with horizontal velocities. Different horizontal velocities. The large object travels like that and hits this place. The small object travels here and hits this. What do you think will happen? Will it take the same time or different time? Now remember, I am now actually giving it different velocities. So suppose I gave this object and this object different velocities. You think they'll still take the same time? Let us see. When I drop, they take the same time. But suppose I push this. Did you hear one sound or two sounds? Obviously this is faster, so it's going to take less time. So you can hear two sounds in case I drop it in one and I throw one. Now Galileo's question is, okay, if I throw it vertically, clearly it is going to be different. And I don't need to do this, I can also do this. One I am going to throw down, one I am going to throw up. What, do you think that they are going to take the same time? No. But Galileo's question was, what will happen if I give them horizontal velocities? Clearly if I give them vertical velocities and different velocities, they won't take the same time. But if they give them horizontal velocities, may not be same time, may not be. So he tried out experiment, because this is not something you can just simply guess. This guy has a velocity 7 meters per second, this fellow has velocity 3 meters per second. Who's going to move more? So who do you think will reach the ground first, and who do you think will reach the ground after that? 7 will reach first or later? Why first? It has more? But it has velocity that way. But it has more distance means it should take more time. But more speed, we don't know. So the basic question is, this may not be answered by just talking. It can only be done by experiments. Okay. So let us try that out. So I am going to take two objects. One is this big basketball and one is this small tennis ball. Okay. So let us take this big basketball and give it a push. And the tennis ball as well, I am going to give it a push. Now I have to make sure it's horizontal velocity. Now if I push it from the ground like this or from the table, then the force will be this way and so it will actually climb up. That's not fair. It should be horizontal. So I am going to push this at the center and I am going to push that at its center. But it will be different velocities. I will give this a small velocity and I will give this a big velocity. Ready? 1, 2. Was it one sound? So it takes the same time. But did it fall at the same place? The faster one went more, but the time it took was the same. That is what is important. Now, after a few experiments, Galileo stopped worrying about the big ball. Well, actually, I don't know whether he did. Maybe he did more with the big ball and small ball, but I am going to stop using the big ball. What I am going to do is I will show this with two small balls. It's easier to see also. Okay. Now, it doesn't matter whether it was a big ball or a small ball, because the mass doesn't really matter. Suppose I had another small ball and I threw this with 5 meters per second, it's going to travel here. Same time. If this takes 3 seconds, that takes 3 seconds, this takes 3 seconds. What if I throw something with 25 meters per second? Horizontally. It will go much, much further and hopefully the ground remains like this. Okay. But though it has traveled so much distance, it still takes 3 seconds. Okay. So we will see this with two tennis balls here. It will be nice to do it with a tennis ball and a basketball and one more tennis ball, but right now let's just concentrate on two tennis balls. One tennis ball I am going to give very small velocity, so where is it going to fall? And the other one I am going to give it a large velocity, so it's going to move like that. Okay? And I hopefully should give this both at the center. Ready? So this is going to be faster. 1, 2, 3. Well, I gave it almost equal velocities. It's hard to give one very much more velocity, but let's try. Ready? 1, 2, 3. Do they hit the ground at the same time? Always, right? So now the key point is, all objects take the same time to hit the ground irrespective of the speed. What if instead of 3 meters per second I had 2 meters per second? It will hit here, but how much time? Same time. What if I gave it 0 meters per second? Same time. But you already know how to solve this problem with 0 meters per second. Because if it's 0 meters per second, you know that it is straight line motion. Because if I don't give it any horizontal velocity, what is it? It is this. But this is what we have been doing all this time. So Galileo had this idea that I can find the time it takes for this guy to fall by not doing this problem at all, but by just simply asking how long will this guy take to fall. Do you understand the connection of this thing? It's a very powerful idea. And then he had the same principle that he did for the earlier one, he extended. He says, how do these balls know that the ground is here? No idea. What if the ground was there? They'll still hit at the same time. What if the ground was there? They'll still hit at the same time. That means when this zero horizontal velocity, which means dropped ball, reaches this place, maybe after 1 second, where will this 3 meter per second ball be? Will it be at the same place? It will be at the same level, same height. Why? Because that guy will also fallen the same amount. Because I could have set the ground here. You can't make the ground like this. That's not fair. Okay, but assuming the ground is horizontal and you're lifting it up horizontally, you can set it wherever you want. So the 3 meter per second ball will be at this level, 5 meter per second ball will be there, 25 meter per second ball will also be at the same level. Except the 25 meter per second ball would have also moved a lot more horizontally. Clear? Everybody comes down by the same amount in the same time, but some of them may move like that, lot more, some of them will move less that way. What decides how fast, how much they will move that way? Their horizontal velocity. So what did the horizontal velocities do to their vertical movement? Nothing. No horizontal movement, same vertical movement. No horizontal velocity, same vertical movement. 25 meters per second horizontal velocity, same vertical movement. 7 meters per second horizontal velocity, same vertical movement. So then he said, horizontal velocity does not affect, well, first of all, it does not affect time of motion, but it also does not affect where you are. So if you take any time interval, it does not affect the displacement, which means at this point, from this time to this time, this guy would have moved this much, this guy also would move this much, everybody will move the same amount. So for the same amount of time, everybody moves the same amount means everybody must have the same velocity, vertical velocity. It does not affect vertical velocity, it does not affect vertical displacement, it does not affect time of motion, does not affect vertical motion completely. Whatever is happening in the vertical motion direction. So horizontal motion does not affect vertical motion. Horizontal velocity does not affect vertical motion. I hope the idea is first clear. It's a very powerful idea. Coming out of one simple thing that if I throw two balls at different velocities, horizontally they hit the ground at the same time. Now that requires experiment, the rest of it requires using the experiment. Right. And how is Galileo going to use this for problem solving? If I want to know how long will this 25 meter per second ball take to hit the ground, don't answer the question. Answer what question? Imagine another ball that is being dropped. How long will that fellow take to hit the ground? That you know how to find. That is the same time as this. Is everybody clear about this idea? Then Galileo said, okay, that's all fine. But how far away has it traveled? You understand the question? They are not traveling the same amount. How far away has it traveled? So here is the interesting idea. And by the way, this requires another experiment which we will right now not worry about. But he had a simple statement, simple idea. Suppose I could switch off gravity. What will happen to the 7 meter per second ball? It will keep moving like this. What will happen to the 25 meter per second ball? What will happen to the 3 meter per second ball? Everybody is moving straight. What will happen to the 0 meter per second ball? It will just hang there. Because there is no gravity, nobody will come down. But do you know that if it takes 3 seconds to hit the ground, in those 3 seconds, this 25 meter per second ball, how much do you think it would have moved? 75. Why? Because there is no acceleration, there is nothing. It is going to move straight. So it will keep moving straight. But right now, horizontal velocity does not affect vertical motion. Do you think vertical acceleration will affect horizontal motion? May. Okay, he needed an experiment to show that it doesn't. But we will right now assume that it doesn't. Okay. Now, if you assume it doesn't, then you can think of switching off gravity. This ball will travel for 3 seconds. In 3 seconds, it will be here. Of course, it won't hit the ground because there is no gravity. 4th second, it will keep going, keep going, keep going. But in 3 seconds, it will be here. And how far will that be? 75 meters. And this ball, the 7 meter per second ball, in 3 seconds will be there. And how much will that be? 21 meters. I have not drawn it to scale. If that is 21 meters, this cannot be 75 meters. Okay, but we'll just ignore it. I can't draw 75 meters on this board. So the basic idea is clear. If there is no gravity, it's quite clear that this fellow will travel 21 meters and that will travel 75 meters. In 1 second, this guy would have traveled 7 meters and this guy would have traveled 25 meters. 2 seconds, the first one would have traveled 14 and this would have traveled 50, and so on. They'll just keep moving as they're supposed to move. Then Galileo's point was, actually, even with gravity, even when there is gravity pulling it down, this ball will continue to go there, but on top of it, just like that ball will continue to hang around, and because of gravity comes down. How much does it come down by in 3 seconds? This much. In 1 second, how much? This much. So in 1 second, if you ask the question, where is this 7 meter per second ball? The 7 meter per second ball will be here, right? Which is 7 meters. The 25 meter per second ball will be somewhere here, which is 25 meters. That's where it should have been without gravity. Now, because of gravity, it has further come down. It is here because it has moved horizontally, assuming there was no gravity. From wherever it was supposed to be, it has come down by the same amount. In 2 seconds, it would have, if this fellow comes down till here, in 2 seconds, everybody will come down by the same amount. In 3 seconds, you know that this fellow comes here. In 3 seconds, this is where the ball should have been if there was no gravity. But there is gravity. So in 3 seconds, that guy will come down because there is gravity. In 3 seconds, this guy will come down because there is gravity. So this guy will be here. What will be this distance? 75 meters. Why? Because that fellow is traveling 75 meters and then coming down. Of course, it doesn't ever happen like that. How many of you have seen Tom and Jerry cartoons? Okay. So in Tom and Jerry, many times, obviously Jerry wins most of the time, right? So sometimes what happens is this Tom flies off. And then he's happily flying, and then as he's flying straight, he's never falling down. Then he looks around and there's this bird flying. I don't know if you've seen this. Then he looks at the bird, he actually says, waves to the bird, he looks around, there are clouds all around. Suddenly wakes up and says, wait a minute, where am I? And then comes down like this, right? It's quite a funny scene. Actually the reason it is funny is because Tom is moving like this and then suddenly moving like this. But if Tom was moving with that velocity, the way it's calculated, he would have been here. You know that Tom actually doesn't move like this. He should have been moving like this. The same thing is now being represented like this. The reason he suddenly comes down, he will move like this and then why is it why can't he come down slowly? Because he's supposed to be here and he's reaching where he's supposed to be in this path, and that looks funny because it's obviously not the way it is going to work. But the point is the final answer is still the same. This is where he's supposed to be. And what Galileo's argument was is that you can study this motion as a combination. This guy is moving horizontally and then vertically. It's not like it was moving horizontally for 3 seconds and it takes 3 more seconds to do vertically. It's not like it went 75 meters in 3 seconds plus 3 seconds to do this. During the same 3 seconds, it came down by this. Happened together. So obviously it never went like this and then like this, but we can analyze it by saying it is this motion plus this motion. Now that motion is really easy. What is it? Uniform motion. You switch off gravity, it's moving in a nice straight line with constant velocity. This motion is equally easy because it's like a ball that is dropped. So uniform accelerated motion in a straight line. So you do this plus this and you know where it is. You do this plus this, you know where it is. If you want to know where is this after 2 seconds, you can't go down because in those 2 seconds this guy would have gone that way, right? So in 2 seconds this guy will be somewhere there and you have to go down like this, or maybe somewhere here and you'll have to go down like this. Why is this object here? Because it has moved horizontally for 2 seconds and in those 2 seconds it also came down vertically. Anyway, we will come back and analyze with certain things. We'll do a few problems using this. Just keep in mind that if I throw 2 objects horizontally, the time it takes for the first fellow to hit the ground is the same as the time it takes the second fellow to hit the ground. If I threw them simultaneously, they will hit the ground together. What if I threw the first one today, it took 4 seconds, I come and throw the second one from the same place tomorrow. How long will that take? 4 seconds. Will they hit the ground together? No, because one is being thrown 1 day later. Okay, but they will still take 4 seconds, 4 seconds. If you threw them together, they will take the same time and you will see that they will hit the ground together. But the time taken is the same. And it is the same even if you just dropped it like this. Okay. When a ball is dropped from the roof of a building, it takes 6 seconds to hit the ground. So here is a building. When it is dropped from there, it takes 6 seconds to hit the ground. When the same ball is thrown from the same place with a horizontal velocity of 10 meters per second, okay, how much time will it take to hit the ground? It will take 6 seconds to hit the ground. 6 seconds because it's going to take the same time. How far away will it hit the ground? Well, for those 6 seconds, it's going to travel like this, right, horizontally. Imagine the entire motion as a combination of horizontal motion and vertical motion. Switch off gravity, this fellow is going to travel for 6 seconds like this. Except when you switch off gravity, there is no speciality for 6 seconds. It won't hit the ground. It will keep going. 5 seconds, it will be here. 4 seconds, it would be there. 3 seconds, it would be there. So what is special about 6 seconds? That is going to come from the vertical motion. Because when it is 6 seconds, the vertical ball, think of the horizontal, the actual ball falls like that. Think of this actual ball as a combination of one vertical ghost ball and a horizontal ghost ball. Imagine 2 different balls. So this one splits up. There is a corresponding ball sitting there and a corresponding ball sitting here. These 2 fellows come back and join and become this ball. Imagine it like this. This fellow does not actually care about when the object hits the ground. It just continues to move with a constant rate. So if this fellow is going to hit the ground, obviously that fellow has also hit the ground. They are part of the same ball. Okay. How long does this fellow take to hit the ground? 6 seconds. Why? Because this fellow takes 6 seconds to hit the ground. Now, in those 6 seconds, it has moved horizontally as if there was no gravity. So, 10 into 6, 60 meters. So, that is 60 meters. But it has fallen down vertically by some amount. So, that means this point is also 60 meters away. So, it falls horizontally 60 meters from the base of the building. Yes? How high would this be? What is the height of the building? Well, half into g into t square, or 5 into 6 into 6. So, this is 30 into 6, 180 meters. 36 into 5, which is 180 meters. Okay. So, it's a very tall building, 180 meters tall. It's quite a lot of height. So, remember that in this entire thing, we are neglecting air resistance. Now, with 180 meters, it's actually hard to claim that there is no air resistance, but we will neglect it anyway. For calculations like this, we are going to assume there is no air. We are also going to assume that all these things are thrown not with 1000 meters per second speed or 10,000 meters per second speed. They are going to be thrown with reasonable speeds such that you can assume that Earth is flat. Why? Because if I start throwing from here, this falls here, this falls there, that falls there. After a point, the Earth curves. Because Earth is not a flat object, right? It's obviously a, is it circular? Spherical. It's a spherical object, right? So, since it's a spherical object, what is going to happen is after some time, whichever direction you throw, you are going to find that it's going to do this. Are you thinking that this time and that time will be the same? And not just that, if it starts to curve, remember gravitational acceleration is this way, but when I start going here, it is this way. There is a change in direction. Even if you assume the magnitude was the same, there is a change in direction. So, we cannot use what we have just learned to analyze a problem where something is thrown from India to Africa or India to London. From Chennai to London, if something is being projected, you can't use this to solve. Why? Because it starts off, you can talk about acceleration being like this, but after some time it's going to go that way and acceleration is this way because Earth has started to curve. Earth is always curving, but that's the basic idea. Secondly, we are going to assume that these heights are not so high up. 180 meters is still fine. Even 1000 meters is still fine. But suppose I tell you that I am moving up 3000 kilometers. Now, gravity will be there, but Earth's radius is 6400 kilometers. 3000 is half of Earth's radius. 3000 kilometers would be almost like half of Earth's radius. Gravity starts to change significantly. Up to 1 or 2 kilometers, even 10 kilometers, acceleration due to gravity will remain almost the same. We can ignore the fact that it has a small change. Okay. Anyway, 9.8 we are going to call it 10. You are not making too much of a mistake compared to that. But if I am going up 6000 kilometers, 3000 kilometers, then thousands of kilometers, then clearly acceleration due to gravity will be different. So, you can't use this to analyze it. So, we are making a few assumptions. So, near the surface of the Earth and at speeds where you are not going across the globe, and for reasonable speeds such that we can ignore air resistance. If it was really high speed, air resistance will start to matter, then this won't work. But we will pretend sometimes as if it works even when you have very high speeds. Okay. For example, we know that whatever this thing time of fall is equal to the time of fall for that, right? What if I shoot a bullet? What do you think about that situation? So, the question is, what Galileo is saying is, if I drop a ball, the ball falls like this. If I throw a ball, the ball falls like that. This takes 3 seconds, that takes 3 seconds, 3, 2, whatever time. Now, if I take a gun here and I shoot, the bullet moves with 100 meters per second speed. This guy is moving at 3 meters per second speed. This is moving at 0 in the beginning. But 100, all of them are horizontal velocities. Now, this bullet is going to travel a long distance. In fact, it will keep going, keep going, keep going, keep going, keep going, and it is going to hit the ground there. Okay, that's a really long distance. Which do you think will hit the ground first? All at the same time, including this bullet. This bullet has traveled a huge distance, but it has a high speed. Actually, what you should keep in mind is in 3 seconds, the bullet would have traveled 300 meters. The bullet should be here, but instead of being here, it is actually there. Now, this is the extra that gravity has contributed. What gravity did to the bullet, the gravity did to this fellow. Because this guy in 3 seconds will be here. But instead of being there, it has come down. In 3 seconds, the drop ball, if there was no gravity, would have remained there, and instead it has come down. Okay. Now, obviously, for these two, probably it is correct. What do you think about the bullet? Do you think at that kind of speed, air resistance will not matter? It will matter. Okay. But if we ignore it, then this statement will be true. In reality, what do you think? The statement won't be true, because the bullet will feel a lot more air resistance because there is air here. But if this happened on the moon, G won't be 10 or 9.8. But whatever the G is, since there is no air, this will work much better there. Or we'll assume that right now on Earth it works, we have removed air. So we are all suffocating, but we are observing how this is working. Okay. If a football is kicked from the roof of a building, a football is kicked from the roof of a building with a horizontal velocity of 17 meters per second. The building height is 20 meters. How much time does the football take to hit the ground, and how far away does it hit the ground? Suppose you want to find that. First point, this guy goes like this. Now imagine a corresponding ball which is just simply dropped. Now that ball starts with 0 and comes down. You know that if this ball is dropped, t seconds is going to go 5t square. So 5t square must be 20. So t square must be 4, t must be equal to 2. T is 2 seconds for whom? For this ball. But the time for this ball and the time for that ball is the same. So this ball also takes 2 seconds. But the time that this ball is traveling is the same time this ball would have traveled if there was no gravity, just right above it, right? So therefore, what would that distance be? 34 meters. So how far away will it hit from the base? 34 meters. Okay, I know that's not asked in that question, but you can always, once you have found this far, you can actually just simply find out what is the distance. Is that clear to everybody? A ball rolls off a table. Rolls off means it's actually rolling off like that. So that means it's going to go off horizontally. Rolls off a table of height 0.45 meters. What is its vertical velocity when it's rolling off? 0. It only has a horizontal velocity. Do you know the horizontal velocity? No. It hits the floor. It hits the floor 0.3 meters away. You know where it hits. Okay? How much time did the ball travel in air before hitting the floor? Well, I don't care about this part. If I drop a ball, how much ever time that takes is the amount of time this will take. Now you know that this must be 5t square, because you already know that this is going to travel for t seconds. Initial velocity for that ball is 0 because it was just dropped. So it's going to take 5t square is the displacement that it's going to have. So 5t square must be 0.45. T square must be 0.09. And root of 0.09 is 0.3 seconds. So it was traveling for 0.3 seconds. Now remember, 0.09 root is not 0.03. It is 0.3. Okay. So this is 0.3 seconds. This is 0.3 seconds. So So this must be 0.3 seconds. But you already know it's traveling 0.3 meters. So if I traveled 0.3 meters in 0.3 seconds, what must have been my horizontal speed? 1 meter per second. So what speed did this fellow roll off with? 1 meter per second. Is that clear?